Right, hello everyone. Let's start with the editorial for today's contest. Today's contest is by, I hope I can pronounce his name, Dixon, Colin Gao, Sung-Yan Chen, and their friends. The on-site winner for this contest, personal, is University of Waterloo Beck. Congratulations to the team. And there are three problems that were not solved by any team. Those are problems F, I, and J. So let's go to the actual editorial. First problem is problem M, and this problem is probably the most problematic in this contest. So in this problem you are given n segments. Each segment has a length L1, etc. at n, and you are asked to find the smallest value of k such that the values 0, k, 2k, 3k, etc. So this arithmetic progression, those are all on the ends of the segment. So in other words, we have if we have segments like this, then for example we may find some k such that here we have 1k, here 2k, and here 3k. So it is important that within each segment of length k, there is a whole group of segments from the input that fit inside. So, for example, if here there was a segment that goes over the boundary of length k, this will be forbidden. So, the solution to this problem is basically just to implement this check. So, first of all, we notice that the answer is always yeah. Sorry? What lights?
What about you?
Do you want to switch them on?
Yeah.
I suppose we can barely do, but I think there might be some issue with the screen because there is some light on top that would be harder for people to watch. So I hope that the people still manage to recognize what I write here. But anyway, so let's back to the problem. So first of all, we notice that the answer is always one of the previous sums, because for the first k, like the sum of the segments that go up to this first value of k, it must be the basic sum of the given segments, because we can't rearrange them. So essentially we go over all these prefix sums, and then we store all the other prefix sums in some kind of hash map, for example, and then we check the numbers 2k, 3k, etc. And if we find any discrepancy, then we stop and we continue to check for the next value of k. So now the harder part is to estimate how much time we return. So like the crude estimate is that in the really worst case, each prefix would be checked by all of its divisors, and like in the worst case, if we look at the values up to 2 times 10 to the power 15, it could be that the number of divisors is up to 2 times 10 to the power 4. So in the worst case, it would be also multiplied by 2 times 10 to the power 5. So in the worst case, it would be a few billion. It is nowhere near to how much it takes in practice, because on practice it's most likely that the most actual type estimate that we can get in practice is an operation n, and because that any solution that works like this would run very fast. So the questions: did anyone implement something else with a probably better complexity? And the other question is, does anyone have an actual proof that this estimate of an operation n works for this setup? Nobody? Well, we also tried our best to find some kind of proof for this, but it seems to be difficult. So yeah, sometimes we have to work with problems like this. So any questions to this problem? Right, let's move on to the next problem. Next problem is problem D. In problem D, we are given 10 to the power 5 sandworms, and each sandworm is represented by some kind of segment from A to R, and we are said that each sandworm is moving to the right with speed vi. That means that after the time t, the first coordinate will increase by t times vi, and the second coordinate will also increase by t times vi. And then we are able to summon at any moment of time. We are given initially the position x where we are standing, and at any moment of time we can choose this time t, and we can summon the shortest sandworm that is currently passing underneath us. So and the problem asks what is the longest sandworm that we may summon under this setup. So this is mostly an implementation / three-line problem. So first of all, we consider each sandworm independently, and for each sandworm we find the segment of time during which this sandworm is beneath us. So there's some segment from L to Ti, which we can find by solving some linear equation. After that, there are several approaches on how to proceed. For example, we could sort all the sandworms in decreasing order by their length, and then in this order we assign this length to the interval that corresponds to the time during which the sandworm can be summoned. And after that, after we process all sandworms like this, for any specific point in time, we can find out which length of the sandworm will be the shortest one if we summon it during this point of time. So we check all the endpoints of the segments, and then we take the largest value that would be the answer to the problem. So this one approach. Another approach is that, for example, we just go over all the again endpoints of these segments from left to right, and we maintain in a set, for example, or some similar data structure, the set of sandworms that covers the currently open segment. So after that, whenever we reach an endpoint, we check the sandworm with the shortest length, and this is one of the candidates for the answer, and then we just output the maximum value in the actual answer, and then this solves the problem. So any questions for problem B? Any other approaches? Right? Let's move to the next problem. Next problem is about a favorite topic of Northeastern Eurasia regional context of OCPC, about some problems on cacti. So in this problem you are given a cactus, which is a graph in which every edge is contained in at most one simple cycle. So it means that the graph would start like this. Like component of the tree is a cycle, and they are connected by either bridges or tap points, like here. So this is what a cactus is. We are given for every edge a so-called lifetime di, which is the length of a time interval that we can keep the cactus active for this amount of time. After that, for each edge, we may pick some start activation time Si, and then we are saying that the edge is active from time Si to time Si plus di. And after that, we are asked to first of all start some edges at time 0 in such a way that the graph is connected at time 0, and after that we need to schedule starting time for all other edges in such a way that the graph is kept connected for as long as possible. So let's go to the solution. So first of all, you should notice that we can just process every deconnected component independently, because if we can keep every deconnected component connected, and we also keep all the bridges, which are also a generic case of deconnected components, then the whole graph will be connected and well. So, and then if you look at each deconnected component individually, each deconnected component will be either a cycle or it will be a single edge which is a bridge in the graph. So, and then we have a bit of casework here, like to keep the bridge alive, we just have to include it from the start and keep it for this amount of time, and then to keep a cycle of length 2 alive, we just must use first one edge, and then when it turns out we need to switch to another edge, so we can maintain it for time d1 plus d2. And if we have some larger cycle with m edges, with lifetime d1, d2, etc. dm, then the answer to how long we can keep the cycle alive is the minimum of d1 plus d2 and d3. Because to keep the cycle connected, we need at any point of time to keep n minus 1 edge active. So and it means that after the certain point can only disable one edge, which for example means that after the edge with the shortest lifetime runs out, we can substitute it with the second shortest lifetime edge, and otherwise all the other edges that go after them, they must stay active, and we wouldn't be able to extend the lifetime of the cycle after that. So because of this, it is the minimum of either the first two edges or the third smallest edge. So we process this for every cycle individually, and after that we output the minimum of all the values over all the biconnected components. And like generally, because the graph is a cycle, we don't need to like implement all the difficult stuff about finding actual general deconnected components in a graph, but rather we can just, for example, do a depth first search, and whenever we find a back edge, we can just maintain the current find edges in a stack, and when we find an edge, we just trace back in the stack until we find the other endpoint of the edge, and this works in linear time because the cycles in a calculus do not intersect, so overall it will be like the total size of all cycles in the calculus. So, and this is also the way that we can solve this problem. So, any questions to problem K? Right? Let's move on. Yeah, next problem was placed as the fourth hardest, as the fourth easiest by the author. And like, if you manage to actually read the problem statement, you will figure out that it is indeed quite an easy problem, but the hardest part is to actually go through these complicated statements with all the different time points that if you read carefully, you will just notice that the time points do not really matter and you can ignore them. So if we summarize this problem in a very concise manner, we can say that there are n conferences up to 5,000, and the ith conference has some interval that it accepts submissions from day Ri to day Di, and after that, after the submission time is over, it announces decision on some specific time on day Ti. The specific time does not matter because this day is after it finishes taking submissions. So, and also each conference has like a parameter which is the impact factor of this conference. And we are told that if we submit some specific paper to the i's conference, and this is the case submission for this specific paper, then the probability that this paper will be accepted is the minimum of 1 and k over wi, where wi is the impact factor of the conference. So now, going further, we are given information about m papers that we have prepared and that we would like to submit to those conferences. We know that for each paper we will finish it on days F1, etc., Fm, again at some specific times that doesn't matter because of how the times are structured. So, and after that, when we finish the paper, if there is no conference at all that's available on this day, then we get upset with this paper. We think that the paper is complete garbage and we throw it away. If there are any conferences that accept submissions at this time, we submit the paper to the conference with the highest impact factor. I'm not sure if there was any type. It was also told that all the impact factors are distinct. So because of this, it is always uniquely defined where exactly we will submit the paper. So we submit the paper to the conference, and after that we wait for the conference to decide on whether the conference accepts this paper or it rejects it. Now, when we have a decision, if the conference accepts this paper, we are happy about it, and we add the impact factor of the conference to our score. And if the conference rejects the paper, then we of course try to submit it to some other conference using the same algorithm that we used when we just finished the paper. And after all that, what we are asked to do is we are asked to find the expected value of the sum of impact factors over all conferences to which we managed to actually submit the paper and get it accepted. So now let's get to the solution. So first of all, you should notice that essentially the final impact factor of a paper, and then with the path that it can travel, it only depends on the first conference that this paper was submitted to. Because after that, the next time the paper will be submitted, if it must to be submitted, will be at the time ti, where the first conference made a decision, and at that time ti, there is a uniquely defined conference that will accept the paper at that specific time, and so on. So because of this, what we can do is we can find an expected impact of a submission to conference number I under the condition that it is the case time that we submit the paper at some conference. And then we have this simple recurrence that the expected value is the probability that the paper is accepted at this specific submission, which is the formula from the statement, minimum of 1 and k over wi. So times the impact factor plus probability that is rejected times the expected value of the next conference, and for the next conference we also increase the index of submission by 1. So we have this recurrence for dynamic programming, and we can just use this recurrence, like we find the next conference for each conference, like j for each I, and then we can find the recurrence in n squared, and then we also go over all possible submission times and also over all times where we finish the papers with a split line, and then we are able to solve the whole problem in time n squared plus m logarithm n. And yeah, this is essentially it. Are there any questions to this problem? Alright, let's move on. Next problem is problem A. In problem A, we are given a tree structure of some prefix tree. So the prefix tree is some tree where on each edge we have a character like AB, and we must maintain that the children of each vertex have distinct characters for all edges. So we are not given the labels on the edges, but we are given the tree structure of the tree. So we are only given for each node in the tree the parent of this node. And after that, we are asked to assign labels in such a manner that the strings that created this tree are discographically smaller. So in other words, like we look at all feathers from the roots to the leaves of the tree. These are the strings that compose the tree, and then we need to assign the labels in such a manner that if we sort the sequence of these things lexicographically, then this sequence will also be lexicographically smallest compared to all other possible sequences that can create this tree. So for this problem, we may notice that, like, because we are bothered mostly with lexicographical ordering, we can mostly solve it greedily, which means that we can go from bottom to the top, and at every time, like, if we consider this specific vertex, the whole subtree of this vertex is independent from anything else. So, like, we can put anything here, and this will not contradict the fact that we are able to make a tree out of the remaining part. So, because of this, for every subtree, we must make sure that the set of pairs to the leaves of this subtree is also lexicographically smaller. So in other words, we do it recursively, and after we return from the children of some specific node V, we essentially just need to assign labels from 1 to k to the children of this node in such a manner that the resulting set of sequences is also lexicographically smaller. So now for this, we of course need to sort the subtrees lexicographically, but like if we are careful about how exactly the lexicographical comparison is defined, we will notice that when we sort, we also need to put in regular lexicographic ordering, when we have two things and one is shorter than another, then we need to put the shorter first. But if we compare the sequences and we think about prepending them with a specific character, we actually would like to put the longer sequence first. So what I need here is, let's say that we have two children. One child is composed of strings A, B, and C, and the other is composed of string A. So, and what we need to do is we need to prepend A to all the sequences from one child, and B to all the sequences from the other child. So we have two options how to do this. We either do AA, AB, AC, and then BA, or we do it like AA, BA, BB, BC. So as you can see, in this case, this sequence is actually lexicographically smaller than the other sequence. So because of this, we need to care about lexicographic ordering, but if one of them is a prefix of another, then we need to put the longer one first. And this is the only cornerstone in this problem. Other than that, we can, if we are given two subtrees, we can compare this sequence lexicographically in the size of the smaller subtree, basically in a manner that is very similar to how if you have two things, you can also compare them lexicographically by the size of the smallest thing. So we use this fact to merge, well, not merge, but essentially we just, every time when we need to compare two trees, we compare them in the time that takes that is proportionate to the size of the smaller tree, and then by the small to large reasoning, we can prove that the total complexity of this procedure will be equal to m logarithm squared n. So now the author also claims that it is possible to fully optimize it to m logarithm m. I didn't look much further into that approach, but you can read about it in the text editorial. And yeah, this should be it for this problem. Are there any questions to problem A? Did anyone solve this problem? Did you use the same approach?
I think I'm one guy.
Some of them. And how did you optimize?
Just like like do it from bottom up, and then every single time we process like a bunch of frequency in a row, we'll reassign them new indices.
Right?
Okay, every single time we process a bunch of things in the same row, we reassign them like new values, like integers, where like each piece of integer if they're like equal, and one piece of a small integer if it's like try to have smaller numbers like to the head, and then we just continue that going upwards.
So you assign an integer to the whole tree.
To each subtree.
Each tree. Like
At the same depth. And then we process the like level above them, and we reassign integers again.
So because of this, like you, when you need to sort stuff, you only sort like sequence of just integers, right?
Or do you do that? I don't know. Maybe it's lost way.
Maybe what?
Maybe it's lost way, not lost, but it feels pretty good.
Alright, I see. Well, yes? Sorry? I'm not sure. I mean, can you just like write a comparator and choose CCP sort?
Yeah, you reassign it as a comparator.
Alright, so let's move to the next problem. Next problem is problem G. Again, a game about quantum computing chickens. I'm not sure what exactly quantum computing chicken is, but I suppose they exist in China. We consider a version of a new game in which a player must always take from the largest file, and then we need to process some queries about this kind of game in a dynamic set S. And we need to respond to two kinds of queries. First query is we add some amount of copies of specific size of file to the set S, multi-set S, and the other kind of query is that we take an intersection of the current set with some segment from L to R, and then with probability 1/2, we take it into the actual set of files that we will be using for the actual game. And for every query of type 2, it is important to notice that after we create the subset S prime, we do not substitute S with S prime because we use S prime for the actual query. So, and after each query of type 2, we need to find the probabilities that the first player will win playing this game. So first of all, let's think about what is the criterion for the win for the first player. As it turns out, after some analysis here, the first player wins if and only if the largest value among the piles occurs odd number of times. So why is it so? Because the first player, because on one hand, if you have only one pile, then a first player can just remove everything from this pile, and then the first player will win. Otherwise, the first player can make sure that the other player gets the state in which it is not true. And so now if largest value is not unique, then we can reduce one of the instances of this largest value by 1, and then we will make sure that the other player gets the other state. And on the other hand, if the largest value is actually unique, then we can reduce it to either the second largest value to make sure that it's odd, or to make sure that it's even, or we can reduce the largest pile to 0 if the second largest pile already occurs even number of times. So this is the winning strategy, and then this means that we need to find the probability that when we pick a specific subset, then the largest value will occur exactly odd number of times. So we are given this count CTX for every value of x, and then like if we consider some subset, the number of the reason about the probability we need to divide everything by 2 to the power of the sum of total counts. So this is just divided evenly over all subsets of the interval of interest. And actually, so basically, for every element, we independently choose whether we pick this element or not, and we need to pick the odd subset. So we iterate over k, where k is the largest file that we will take, and then we count the number of subsets of the largest file that contains odd number of elements, which is 2 to the power infinity k minus 1. This is for the largest file, and for everything that is smaller than the largest file, we just consider all possible subsets. So now we can simplify the sum to that expression, which is just some kind of sum of 2 raised to the power that corresponds to the sum of to the sum of counts on the corresponding segment. So, and then when we need to add something to the power, we essentially need to multiply some of the stuff on the segment by 2, and the result can be done using the segment tree. And then we produce to solve the problem. So, are there any questions to problem G? Did anyone solve this problem? Right. You use the same approach? Right, good. So let's move to the next problem. Problem L, love choice. This another problem about probabilities. So generally you may notice that on this content there are a lot of problems that revolve around probabilities. So in this particular problem we have 5,000 questions, and each question has up to 1 billion choices, which is, it has something about latency or something like that. So I suppose this realistic situation that you have 1 billion choices per 5,000 situations. So, and of course exactly one choice is correct. And also for some of these questions there is a hidden choice. And if the question has a hidden choice, of course the correct answer is the one that is hidden. And in this case we also would not be able to choose the hidden answer until we try to choose all the open answers. So so we repeatedly play this game in rounds, and in each round we go over all questions in order. And if we know the correct answer for this question, we will pick this correct answer. Otherwise, we consider all the answers that we don't know about them, whether they are correct or not yet. So we don't pick the answers that we already picked in the past, and we decided that they are not correct. And after that, only if we already exhausted all the open answers and the question has a hidden answer, we will pick the hidden option. So, and for this setup, we are asked to find the expected time that will take us to pick all correct choices to all answers in one round. So first of all, we need to notice that we don't really care about picking them all in one round, because once we know the correct answer, we will always pick the correct answer in all the following rounds. Because of this, we can just independently consider the maximum of times in which we know the correct answer for each individual question. So let's say that x is a random variable that corresponds to this maximum time, and we are asked to find the expected value of x. Now, first of all, you may notice that for any x, the time at which we get the correct answer is larger than the maximum value on one hand it is larger than the maximum number of choices for creating these hidden answers on one hand. On the other hand, it cannot be larger than the maximum number of choices over all questions. So therefore we reduce the interval for the values of this unknown variable to the values to the integers between a and r, and after that we can reformulate the answer as this formula. It is the value of r minus the sum over all possible values k, that k is the k is the vector answer of the probability that we finish before the scale. So this is mostly due to linearity of linear expectation, but on the other hand, if you consider this probability that the maximum of all xi is less or equal than k, then it is essentially, because they are independent, you can say that it is the product of probabilities for each individual xi that is less or equal than k. So we do this, and after that we need to find some expression for what is the value of probability that some specific xi is less or equal than k. So for this, we consider the probability that xi is equal to some specific value t, and for this, it means that we need to pick one of the wrong answers on the first iteration, then one of the wrong answers that remain on the second iteration, etc., up to the fifth iteration, and on the last iteration we must pick the one remaining correct answer. So this is for questions that do not have a hidden answer. And if we look into this expression, there is some kind of corresponding product here, which means that the whole product collapses to just 1 over ai. So in other words, it means that the variable xi as a random value is uniformly distributed on the segment of integers from 1 to ai. So in other words, we can say that the probability that xi is less or equal than k is the minimum of 1 and k over ai. And now we plug it back in. So we have that the expected value is r minus sum over k of the product over ai that is greater or equal than k of the value k over ai. Now we can group together values that have the same. We can group together values of k for which so basically if you consider all ai, right. So if we sort this array, there will be some segment of k's that belong here, some segment of k's that belong here, etc., for which we only care about the number of ai's that are larger than this k, and we also care about the product of ai's that are larger than this k. So for the product we just find some suffix product, and then for the counts we also notice that we also group them together, and we see that the whole problem boils down for a zero count to find the sum over k from some left endpoint to the right endpoint of k raised to the specific power c. And c here is some kind of constant. So now we use some standard approach here. We notice that this sum, if we sum it from k equals 1 to r, it will be a polynomial of degree c plus 1 in the variable r. And then we find this polynomial using the Lagrange interpolation, for example, or any other kind of interpolation or formula. And after that constraints for this are low enough, so we can just find it in n squared and then use it, plug it back in to solve the problem. And that is it. So, any questions to problem L? Right. Let's move on. Next problem is problem B. In problem B, we are given a tree on 1 million vertices, and we are asked to pick a subset of the vertices of this tree, and then when we pick this subset, we directly connect any pair of vertices that don't have another vertex on the path between them in the original tree. And after that, we connect the weight of this new connection is exactly the weight of the pairs that connect them. So after that, what we are asked to do is we are asked to sum over all possible subsets the value of the size of the subset times the cost of picking this subset. And this problem is mostly about DP on trees, and in particular about how we can do rerouting on this. So, first of all, let's investigate what exactly we are asked to sum up, and we will reduce it to some sums that are much easier to work with than the original formulation. So, let's say that we fix some specific distance d, and we consider two edges, two vertices A and B that have the distance d between them, and then it means that in any subset in which the path between these vertices will contribute to the answer, we must not take any vertices that lie on the path between them, which means that we iterate here over the size of the subset for remaining vertices. So here we have two vertices that we already picked, and we pick k vertices on the remaining part of the set. And only n minus d minus 1 vertices are available to pick because we excluded all the vertices that belong to the path between A and B. So we pick k vertices from that, and if we sum this up, using some more or less standard approaches to find up sums with non-of repeating, the whole sum will collapse to d times 2 to the power n minus d minus 2 times n minus d plus 3. So, and after that, we can use this to reformulate the whole answer as 2 to the power n minus 2 times n plus 3 times a minus b, where a is the sum over all pair of vertices of the distance between them times 2 raised to the power minus this distance, and b is the same sum, but we use the distance squared here instead of the original distance. So, and this kind of summation is something that is much easier for us to get from yes. So here we have 2 times n minus 2 times 2 to the power minus d in the upper expression times d times n minus d plus 3. So 2 to the power n minus 2 is this one, 2 to the power minus d is this one, and then we group this into d times n plus 3 minus d squared, and then we plug it back in to the sum over all possible pairs of vertices, and then this reduction. Does that answer the question? Right? So now we are only concerned about computing this value and computing this value. So generally there is something that we often need to compute on some kind of segments, like imagine summing up the values, summing up the square values, and usually what we do is we maintain the sums up to we maintain the sums of all powers up to the largest powers that we care about. So in this case, let's say that we maintain FUK as the sum of d to the power k times 2 to the power minus d, where d is the distance from specific vertex in a subtree of u, and the distance is to the vertex u itself. So if you maintain this kind of values, you can see how they change if you go from some subtree u into some parent v. So what we can see is that we can factor out the contributions of u into v as follows with this formula. So we need to increase d by 1, which is why we replace minus d to minus d plus 1. Here we replace d with d plus 1, and this is also d plus 1 squared, which we can rewrite in the terms of just d squared and 2d and so on. So now, and we also need to add 1/2 to account for the new distance between u and v themselves. So now we have this transition formulas that tell us how much the value of FUK change when we move from a vertex u to its parent v. So we use first we use these transition formulas to compute this kind of dynamic programming all the way to the root of the v. To the root, and then what we do is we do some kind of standard reducing dynamic program, which means that we start with the root, and then we go into its children, and when we go to the child, we subtract the contribution of everything except the child. So, and after that, we will be able to find this sum of distances raised to the power and times 2 minus t for all possible ways to choose a root of the tree. So this is one way to solve this problem. Another way I was told that it is also possible to get some similar calculation formulas if you just compute them not as distances to the root of the tree, but as directly distances from one vertex in a subtree to another vertex in a subtree. But I assume that it is slightly more involved derivation to actually get this formula. So for this reason, we mostly use this rerouting approach as interim solution to the problem. So, are there any questions to problem B? Did anyone solve this? Alright, let's move to the next problem. So problem E, as you may notice, it's somewhere quite far to the right. So the author expected this problem to be quite difficult, and Jim Waterloo solved it in the 24 minutes from the start of the contest, which is quite fast, very impressive. So in this problem, we are given a multiset S that contains values b1, etc., bn, and we do n rounds. In each round, we pick some value bi, this probability that is proportional to bi itself. Then we write them down in a sequence and remove from S. So after that, we are asked to find the expected number of inversions in the final sequence. So if you put it in writing, we need to sum up over all possible pairs of bi less than bj. The probability that bi is picked after bj. So first of all, we can condition this probability on the sum of remaining values when we pick first of these elements. In this case, the probability will be like the probability that some specific element is picked is this element over the sum, and then we have the probability that the maximum element is picked, maximum of bj over s, divided over the sum of probabilities that one of these elements is picked. And we can see here that this over s factor is just factored out. It factors out. So because of this, we see that this probability is actually unconditional. So it means that we just need to find the sum over all bi less than bj of this bj over bi plus bj. and this can be solved with divide and conquer with some kind of convolution stuff. So first of all, we can define the variable Cj, which is the number of the i's that are equal to Cj, and then in terms of this Cj, we can rewrite the whole stuff as Ci Cj times j over I plus j. So here j corresponds to the actual value, and Ci and Cj are the sum. So Ci Cj is the number of pairs that contribute to the sum with the value j over I plus j. So after that, we do divide and conquer on the values of j. So we consider the case where I is from the left half and j is from the right half, and then we can rewrite it as a kind of convolution. So essentially we group them together by the value of I plus j, which is why we divide by k here, and then we just extract the corresponding value in the convolution of these sequences, and then this results in a solution with n logarithm square 10. So there was some complaint that the time limit here is a bit tight. As the author told me, the solution is like very standard convolution. It runs in around 300 milliseconds, which is a bit below 1/3 of the time limit. So that's why the author thought that this kind of time limit will be appropriate for this problem. So yeah, I wanted to ask, so is this problem just easy, or like is it a bit well known, or how did you manage to solve this as a first problem in first half an hour of the contest?
Like, I got the solution in like 2 minutes, and then like I just knew how to like do it.
I see. Yeah, very impressive. That's great. So let's move to the next problem now. Yeah, this problem looks a bit annoying. In this problem we are given a weighted set of n points, and we are asked to delete k points where k is something very small up to 20 in such a manner that the remaining points form a convex polygon, and the total weight of remaining points is as large as possible. So generally, when we are given a set of points and we are asked to compute something about convex polygons that can be formed out of these points, the approach here is basically almost always some kind of dynamic programming on the convex stuff. So that looks like this. We pick some point to be the bottom left of the whole set. After that, we discard the points that go below it, and we sort all the remaining points by the polar angle around the point O, and then our state is like we maintain, for example, this point, and also we care about the previous and the next edges that connect into the next programming. So this is like the general formula here, and let's talk a bit about how to apply it to this particular problem. So first of all, we can connect points I and j with an edge of weight wj, and after that we can sort all, like we can hypothetically sort all edges by their angle. Like we can't really do this because there are too many of them, but we can imagine that we did this just to get any kind of solution. So after that, we can say that the optimal edges that form the actual convex polygon in the answer is a subsequence of all the edges sorted by their angle, and after that we can also brute force the first vertex, the bottom left vertex of the set among first k plus 1 vertices if we sort vertices like cryptographically. So after that, starting with this vertex, we can maintain a dynamic programming Fij, where Fij is the maximum weight that we can obtain if we start at vertex P. After that, we go over some edges, we end at vertex I, and we use j edges along the way. So this is what we care about, because in the end, the answer would be the value of this dynamic again in the point P itself, but with the number of edges that we took, at least n minus k. So, and then when we go over all edges, we can relax, we can propagate the value of this dynamic again. So you take the value of fuj plus the weight of the new vertex, and we try to push it to the value of fv in j plus 1. So this is the approach that will solve this problem in some quadratic kind of time. And it of course wouldn't work on this problem directly because the n is too large, but we need to utilize the fact that k is very small here. So how do we do this? First of all, you notice that we only care about k minus values in this dynamic program for any specific vertex. This first what we need to care about. The second fact is that if we sort all the points around P, around the bottom left point by their polar angle, then the endpoints of consecutive segments in our polygon, they must not lie farther than k plus 1 apart in this sequence, because if they lie farther than that apart, it means that we need to skip this amount of points, and it means that we will not be able to get the needed amount of points in the end. So number of edges that we care about from n squared to n times k, and finally, that's essentially it. So after that, we just note these k-largest values when processing this huge set of edges, and this results in an algorithm that runs in nk squared for any specific choice of the bottom left point P, and so like summed up over all possible choices, we get the algorithm that runs in nk cubed plus n. This is the solution to problem H. Any questions to this problem? Right? Let's move to the next one. This is this problem is also a bit annoying. So we are given an n times m icing with k obstacles, and we can move right and down until we push into obstacle or the boundary. So a very standard setup. We encounter it in many video games all the time. And we need to process a few queries. First query is that we put a new obstacle at some specific point, and the second query is that we need to find the minimum number of moves that we can do to make it in a position that we are not able to make any other move after that from a specific starting point A and B. So this is a problem about maintaining dynamic trees. Like the internal solution uses linked cut tree, but I assume that you could also try to solve it with some kind of tree with extra logarithm factor. I assume. I'm not sure because I didn't implement this. So, so what we need to notice is that there are only n plus m plus q points at which we possibly could stop. So those are the points that are directly adjacent to some of the obstacles, or those could also be some points on the border of the whole ice link. So so now we work with those points and we disregard everything else, and then we can notice that these points, they actually form a forest, because that isn't about some point where we stop. Like we were moving to the right, and at some point we found either the obstacle or a border of the ice rink. So it means that we, from this point, and also we are only allowed to move right or down, which means that in this case, from this point, we will only be able to move down. So essentially, when we have like when we start at some specific point A and B, we can only pick the direction whether we move down or to the right, and starting from there, we can't control anything, because after each stop we will have only one option where to go next. So because of this, we can say that all the key points, they form a forest. If you consider the parent to be the next key point at which we will stop, and what we are asked to do is we are asked to find the distance from some specific vertex to the root of the corresponding tree in this forest. So now the problem asks us to add new obstacles, but if we reason about what happens to the forest when we add new obstacles, like the structural changes there could be quite arbitrary, and it will be hard for us to predict what happens. So because of this, we instead reverse the order. So we assume that from the start we have all obstacles already added, and then our queries are actually not to add new obstacles, but to remove some of the obstacles. And then, if we get some obstacle and we remove them, like what could happen is, first of all, there might appear a new key point at this obstacle. If, for example, there was an obstacle right after it. So there's one possibility. There could also be and also removal of this obstacle could invalidate two previous key points. So if you are able to stop to the left and to the up of this obstacle after we remove it, what will happen is this path will have to continue further to the right, and this path will have to continue further down. So essentially, what we will need to do is we take a tree that is rooted somewhere here, and we reattach it to the next key point that we can reach in this direction. And correspondingly, for the down direction, we take the tree that is rooted somewhere here in the subtree, we remove it from this point, and we reattach the tree to the key point that will be next in this direction later on. So, and we use min-cut tree to maintain all the stuff. And as I understand, this somewhat standard operations on the min-cut tree, and then this solves the problem I. So, any questions to this problem? Did anyone try to solve this problem with fun? Alright. Yeah?
I think about the part we use in the tree, but I just didn't want to.
I mean, yeah, makes sense, reasonable. I wouldn't want to do it either. So, let's move on to the next problem. Next problem is problem F. This is one of the rare suffix structure problems. We don't see them that often in OCPC context these days. So in this problem, we are given n strings, s1, etc., sn, and we are also given a text key. And then we need to process few queries. And for each query, there we describe it in a bit more complicated manner in the statement itself, but this is probably the easier way to look at it. So for each query, we are given some segment L and R, and we need to count the number of numbers k, such that, let me just draw it, just to be easier. Let's say that this our whole text key, and we are given some half open interval from L to R. So what we need to do is we need to find some k such that these two things of length k are equal, and then if you consider this string b that goes from r minus k to the r, then this string b must be a cyclic shift, so it must be cyclically isomorph to one of the input strings s1, etc., sn. So, and of course, with this setup, the solution is essentially some kind of suffix structure bash, which goes like this. So first of all, we can insert all doubled strings from the input in some kind of general suffix automaton, for example. I think you can also try to do it with the suffix tree if you are more confident with it, or even you can try to create a common suffix array for them. So the topic says suffix automaton, but it's really up to you which kind of suffix structure you want to use. In any case, after we will be able to locate every state in suffix automaton for every cyclic shift of each SI. So how do we do this? Like when we have double SI and we insert this string, this double SI into a suffix automaton, for example, one character at a time. So at any moment of time, when, for example, we inserted this character, we know a state in suffix automaton that corresponds to this string, which is the prefix of the whole doubled string S. So after that, what we need to do is we need to jump by suffix links of this state until we get to the state that contains a substring of length Si, and in this manner we will find a state that contains the corresponding cyclic shift of Si. So after that we do this for after every addition of new characters in the second half of the string, and we will be able to mark the states accordingly. So how do we use this? First of all, let's reason about this number k. This number k, from this part of the constraint, any value of k is valid if it is smaller or equal than the largest common prefix of the suffix starting at L and the suffix starting at R. So we can find this largest common prefix of these two things, and this just gives us the lower bound on the length of this string B that must end at the position R. So after that, what we can do is we feed the whole text through the suffix automaton of all the double strings, and then we will able to get a state in the suffix automaton that corresponds to the prefix from 0 to R of the text. And after that, what will happen is that we will need to sum up on the suffix link path of this state up to the root all the marked states that have the length between Ri minus Li minus this maximum k that we got from this estimate as an LCP, and the length must be at most Ri minus Li. So, and then this allows us to solve the problem and answer all the queries. I think that the memory limit would be a bit tight to this problem, but hopefully people will not encounter this, maybe because they don't solve the problem, maybe because EOLINK has a better handling of memory than the polygon. So in any case, we do the stuff and we solve the problem. So essentially, most of what is done here is some more or less standard manipulations on the suffix structures. So, are there any questions to this problem? Yeah?
For getting in the cyclic shift,
Yeah?
you like go forward one character, pop one character. Do you know if like what's the easiest way to like process that in a suffix at runtime? Because like is popping one character from the end is like a jump. You keep jumping on a link until.
Yeah, so when you jump on a link, like you cut off a bunch of characters, right? So how you handle this is you can, for example, maintain a pair, like a state Q and the current length. So after that, for for the state Q, you know the maximum length of the string that contains here, which is the length of the state, and then you know the smallest length of a string that is contained here, which is like the length of the link of Q plus 1. So essentially what you need to do, if you are still in the state, you just decrement this value, and if you need to go to the next state, you go by the substring and update the Q.
Okay.
Right? Any other questions to this problem? Yeah. In this problem, like the suggested solution uses general automaton for double string Si, mostly because the constraints are such that Si are smaller than the total length of T, but I believe that also you would be able to construct a Zurich automaton for T itself and instead fit double string Si into the Zurich automaton of T, and also do this start with the Zurich strings to find the states in T that corresponds to all cyclic shifts of Si. And in this case, it might be easier to work with this because you wouldn't need to reason about what happens when you construct general automatons for several strings at once. So yeah, I think that should be it. So let's move to the next problem. This is the hardest problem of the quantity, problem J. And this problem is about some facade and square root decomposition. So let's discuss the statement first. We are told that there are n circles, and for each circle we know its x coordinate, its y coordinate, and its radius we do not know. But we are told a bunch of facts about the radius, and we have all the facts are like this. Either we are told that the sum of two radii is greater than this gives the result to W. Oh no, it should be the first fact is that the sum of radius is greater or equal than the distance, the Euclidean distance between 2 points, between the centers of the circles. Then the second fact is that the maximum radius of two given circles is greater or equal to W, and the third kind of fact is that the minimum radius of two is less or equal than W, again for some pairs U and V. So now what we are asked to do, we are given additionally some small amount of constraints that we are allowed to add to the first ones, and we need to, and for each constraint we can demand that some specific radius is less or equal than the given value, and we pay PI to use to impose this constraint on the network. And what we want to do, we want to disrupt the network, which means that we want to make the inequalities inconsistent, so that there are no solutions. And at the same time, we want to do it at the minimum cost, considering the cost of adding this constraint. So, and let's talk about how can we solve this. So first of all, we see the constraints of type A and B, they like demand that the circles are bigger. And on the other hand, the constraints of type C and D, they demand that the circles are smaller. So for the constraints of type C, like for constraints of type D, they are already applied to just one circle. But for constraints of type C, we can treat them as to say that either RU is smaller or equal than W, or RV is smaller or equal than W. So we can pick which one of them would we like to satisfy. And there are 2 to the power C ways to check which one we can satisfy theoretically. So if we fix the assignment of which one we want to satisfy, then after that we will have only unary constraints for every individual point. So we will just and all constraints. So we will just take for each point we will assign the maximum possible value because it benefits the constraints of type A and B. And after that And after that, we can check if they are compatible or not, and if yes, and we can use it to decide whether the problem is fixable or not. So, because of this structure, it can hint us that what we should do is to model this selection of which secure constraint will be used. We can model this as a kind of two-sats or two-satisfiability problem. So let's speak in the language of two-sats here. We will use x prime to mark the negation of variable x. Now, for every constraint of type D, we introduce a variable x that is true if the imposed constraint of type D is satisfied. And then we can add to our implication graph the edge x prime to x with weight pi, which means that like if this constraint is not satisfied, then we can enforce this constraint at the cost pi, and then we will use it later in our analysis of the two-sat network. But for now, let's reason about other constraints. So for constraints of type C, we need that either the radius of u or the radius of v is less or equal than w. So we create two variables, x and y, for this fact, and we say that at least one of them must be satisfied, which in the terms of Boolean functions means that if one is not satisfied, then the other must be true. So we create edges from x prime to y and from y prime to x. So this is for constraints, so we only have variables for constraints of type D and type C. Now what we can do further to make our constraint types is for every vertex V, we look at all paths that we created previously, so that xi must be less or equal than some amount of wi. So we sort this path by the constraint, and after that we add this implication that if the type of constraint is true, then the last type constraint must be true as well. And correspondingly, we do it in such direction that if the larger constraint is false, then the smaller constraint must be false as well. Now, for the type B constraint tells us that let's get back to the type B. Type B is this. It says that the maximum radius must be greater or equal than W for some specific pairs. So it means that either first radius must be greater or equal than W, or second radius must be greater or equal than W, but they cannot be satisfied at once. So on the constraints from here, they will violate it for the first variable or for the second variable. So after we sort them, we can pick largest x and largest y, such that if they are true, then the constraint defined by B is violated for the corresponding circle. So, and because only for one of the circles we can violate this constraint, we add the implication that if first constraint is violated, then the other constraint must not be violated, and vice versa. So this is for constraints of type B, and finally for constraints of type A, we also do something similar. We go over all constraints imposed on the first vertex, and we find a largest constraint imposed on the other vertex that would violate the constraint. And we also say that for the problem to be feasible, they must not be violated at once. So we say that if one is true, then the other must be false, and if the other is true, then the first must be false. So and essentially, with this network, we can check if if it is possible to assign, if it is possible to assign the constraint of C to U or V in such a way that all the constraints are satisfied. And if you look at this network, you will see that we have a total of 2C plus D variables, which is fine, this still linear amount. But if we count the edges, you will see that we have D plus C plus D edges for constraints of type B, C, and D, because for D we have one edge, here we have two edges, and for D we also have two edges, but for every constraint of type A, in the worst case, we add we go over all constraints of the larger set, which can be in the worst case up to C plus D, and we add a new edge for each of those constraints. So because of this, we have a quadratic factor here in the number of edges in our implication graph. So the next step that we need to do is to somehow reduce the number of edges in the graph. So for this, we notice that here, when we are processing the constraint of type A, we say that we go over all constraints of one of the circles that are affected by the constraint of type A, and we then find a pair constraint in the other circle. And here, depending on which circle we choose, there might be different amount of new edges that we add, because the amount of new edges corresponds to the amount of edges in the first vertex that we chose here. So because of this, it always makes sense for us to only process the smaller vertex when we create new edges for constraints of type A. So let's say that the size is TDV, as the P, and then we will always process the pairs in the size that is the minimum of them. So let's assume that U has the smaller size than V. Then if the size of U is already less or equal than the square root of M, that means that the total contribution of this kind of vertices to the final number of edges will be at most a square root of M, because there are only square root of M new edges for each of the constraints, and there are 8 constraints for this. So this is one case. Another case is that we have two vertices that both are larger in size than the square root of M. What this means is, on one hand, for the first vertex there are only square root of M distinct possibilities of what is the value of the first vertex. On the other hand, if we sum up the sizes of all other distinct vertices that also have the size M, then those sizes together will sum up to the value of M. So because of this, if we exclude constraints from A that apply to the same pair of vertices and only keep the tightest constraint, it will mean that we can process all the pairs of vertices that are larger than square root of M, while only adding M square root of M new edges. So because of this, after we do it this way, we make sure that the total number of edges that we add on this step is, and the previous step as well, is B plus A plus M times square root of M, which is generally defined under the constraints of this problem. So now we figured out how to construct an implication graph for this problem, which has a reasonable size. And the only issue that we need to resolve now is how to actually find the minimum cost way to make this infeasible. So first of all, let's remove all positive weight edges and find the strongly connected component in the graph after we do this. So we just check if the given constraints are already feasible or not before adding any extra constraints. And this is some standard in how we work with two sets. So if we find out that some variable x and its negation is in the same quadratic component, it means that x follows from not x and not x follows from x, which means that it is not possible to assign a truth value to x in a way that is satisfied. So if this is the case, then we can say that the whole set of constraints is already infeasible. Otherwise, what we need to do is we need to add back some of the positive weight edges in such a way that there would be some cycle that will contain some pair of vertices x and its negation. So what we do here is we consider a subgraph that is HCD subgraph that is induced by only vertices that we created for the constraints of type D, because we will only be adding new edges between these vertices. So for every pair of vertices that corresponds to the D type constraints, what we check is we check whether each such vertex is reachable from every other vertex of type D, and we add an edge if it is true in the corresponding induced subgraph. So we can do this with the set if we just maintain for every vertex in the implication graph the bit set of D-type vertices that are reachable from this vertex in the implication graph. And after that, if we look at the values at the type D vertices, we will be able to use them to construct the induced subgraph. And after that, we will just need to find a minimum weight cycle that contains some variable type D and also its negation. And the cost of this cycle will correspond to the cost that we need to provide to make the whole implication graph infeasible. So, and if we plug all this back into our complexity estimate, we will get this formula that seems to be somewhat reasonable from the runtime point of view for the given constraints, and this will solve the problem J. So, any questions to problem J? Yeah?
Why do you need excessive construction of reachability gap? Or why do you need...
Sorry?
Why do you need excessive construction of reachability? Why?
So we can divide by 54 in the complexity.
It's not something that's just like one bunch of multi-sources here.
Well, it's like you need to run 250 of them, and it's already m square root of m, so probably it's better to reduce the time.
I think this is explaining. So it's like we want to get this subgraph that to be reached by some D difference, like having it start from the D or the C. Or do you care which vertex in the D vertices can reach it, or do you like not care?
So I think that for every two vertices U and V in D, we care whether we can reach V from U and U from V in the original graph.
Oh, okay, yeah.
Any other questions about problem J? Did anyone try to solve it during the contest? Right, I can understand. This problem is actually quite hard. Right, so thanks everyone for coming, and see you next time.